Today we're going to talk about something called radicals. So before we start doing problems, we need to talk about a few vocabulary words. So the first vocabulary word I want you to learn is what the radical sign is. That's that check mark looking sign. This tells us that we're about to take some kind of a root, like a square root or a cube root or something to that effect. The next thing I want to talk about is something called the index. So the index is this little number right inside the crook of the check mark. That tells us what kind of radical we are going to have. So let's see over here. Index tells us what kind of radical you have. So that could be a square root, a cube root, fourth root, fifth root, all the way up to infinity. Then the last part of a radical is the radicand. That's the number inside. The number inside or expression, because you can have variables in there, underneath your radical sign. The expression under the radical sign. Okay? Those are the three parts of a radical. You have the sign, the index, and the radicand. So now we have three kind of roots we're going to talk about. We're going to talk about square roots, which actually have an index of a 2. Now, this one actually isn't shown. So if you don't see an index, you have to know that it's a 2. It's implied. Then we're going to talk about cube roots, which have an index of 3. And we're going to talk about fourth roots, which have an index of 4. So our first example is a square root. And the reason you know it's a square root is because your index, which should be right here in this little crook, is actually missing. So since it's a square root, what's going to happen is that means we are going to simplify pairs of multiplied numbers. So the first thing we need to do is we need to break down this 117 into two numbers that multiplies to give you 117. So 9 times 13 gives me 117. Now when you break apart a number, cross it out. That way you don't reuse it, because 9 times 13 is 117. I have the exact same number, just written a different way. Then we can break 9 down into 3 times 3. Now, 3 times 3 we have to leave because those are both prime numbers. We can't do anything except 3 in itself, or 3 and 1. 13 is also prime. That is just 13 and 1. So since square roots simplify pairs of numbers, what that means is, that means that these two 3's are going to be able to jump out of the square root. And here's why. 3 times 3 makes 9, and we know that the square root of 9 is a 3. That's how it gets simplified out. So only one number goes out of your square root. Then you have your square root symbol, and anything left without a pair, like that 13, stays inside. So the simplified version of square root of 117 is 3 times the square root of 13. So pairs go out, and singles stay in. Pairs go out, singles stay in. Now let's try it with a cube root. So cube root, the process itself is not changing. The only difference is this simplifies groups of 3 numbers multiplied together because the index is a 3. Again, we know it's a cube root because we have this index of a 3 right here. This one is a little different than example 1 because there's a 2 hanging out in the front and being multiplied to this cube root of 48. So we're going to hold off on this 2 until the very end. So let's start the cube root of 48 just like we started the square root of 117 and break 48 apart. There's a lot of numbers you can break 48 down into. I usually think of 6 times 8 first. You could have also done 2 times 24. Okay, anything will work as long as you break everything apart as far as it goes. 6 gets broken down into 3 times 2, and those are both prime, so I can't break those down any further. 8 gets broken down into 2 times 4. 4 can break down into 2 times 2. Now, since this is a cube root, we need groups of 3. So I see I have 3 2's all multiplied together. So that's one group of 2's that I'm going to be able to take out of my cube root. Now, yes, there is another 2 here, but because I don't have enough to make another group of 3 2's, this one's stuck on its own. So, just like the square roots, this pair or group of 2's are going to come out of my cube root. Then, inside the cube root is going to be a 3 times a 2 back inside. Now, this is where we're going to bring down this 2 in the very beginning. Now, the 2 is being multiplied to the cube root of 48. Well, this is the cube root of 48, just written differently. So what we're going to do is we're going to take this 2 and we're going to drop it way down into the front because he still matters. Now that everything is in its place, we're going to take everything and simplify. So on the outside, I have 2 times 2 makes a 4. Then I have the cube root of 3 times 2 makes 6. So 2 times the cube root of 48 is equal to 4 times the cube root of 6. Simplifying it down means use smaller numbers instead of larger ones. Get as much out of that root as you can. Example 4. Well, fourth roots is the next step we're going to do. This is the only 3 we're actually going to talk about because the pattern remains the same no matter which root you have. So we know this is a fourth root because of this index of a 4 right here. And that means you're going to take out groups of 4 numbers that are multiplied together. So same way as we did the square root and the cube root, we're going to ignore the 3 in the front first, and we're going to break apart this 162. Now, I went and divided it by 2 because I knew it was even. So 2 times 81 gives me 162. Then 2 is prime, but 81 I can break down into 9 times 9. Both 9s can I break down into 3 times 3. Okay, now that everything's broken down into primes, we want groups of 4 sets of numbers. So I see there's 4 3s right here. That's a group. Because it's a fourth root, you need groups of 4 things. Cube roots need groups of 3 things, and square roots that don't have an index need groups of 2 things. Now that we have our groups, what is in a group goes out of the root. So 1, 3, like a representative, not 4 3s, just 1, go out of my fourth root. And then what's left without a group, so this 2 way up at the top stays in the root. But we can't forget about this 3 in the very front. That 3 is still being multiplied out front here, like so. So then we're going to simplify this all down. 3 times 3 makes 9. And then the fourth root of 2 is my simplified version. Okay, let's try another one. So we have a negative. So remember way back when we solved quadratics, we talked about negatives being inside square roots. That wasn't okay because you could never get a number times itself to give you a negative. But this is a cube. That's a little different. So let's break this apart this way. So for this cube root, we're going to break down negative 250. I'm going to pull the negative 1 to the side and pull the positive 250. Because negative 1 times 250 does make negative 250. Negative 1's prime, so we're going to leave him alone. 250, I can do 25 times 10. 25 can be 5 times 5. And 10 can be 5 times 2. So, because this is a cube root, we're looking for groups of 3. 3 numbers. So I have 5 times 5 times 5. That's my group of 3 numbers. So the 5 is going to come out of the cube root, and what I have left is negative 1 times 2 underneath. Now, let's think about this negative 1 right here. So a cube root is asking you what times itself 3 times gives you that number. So if I look at just the cube root of negative 1, let's think about that. Cube root of negative 1. Well, doesn't negative 1 times negative 1 times negative 1 still equal negative 1? So that means this is a perfect cube. It's a perfect cube. This cube root of negative 1 is actually equal to negative 1. So I can simplify this little piece even further. So what you're going to have is you're going to have the 5 outside that we had from simplifying. Then you're going to have times negative 1 because that's what the cube root of negative 1 is. Then times the cube root of 2 because there's nothing times itself 3 times that gives me a 2. Then let's clean this up. 5 times negative 1 makes negative 5. Cube root of 2. There's my simplified version. So if you have a negative underneath a cube root, it's just equal to negative 1. A negative underneath a square root is an imaginary number. That's the I. So it's a little bit different. Let's try one with variables. So we have to first determine which kind of root this is. So that's looking at the index. Well, in this one, there is no index right here. So that means the index is a 2. So that means it's a square root. So we want pairs of numbers. So break apart your 32 just like normal. So 32 can be 2 times 16. You could have also done 8 times 4. Doesn't matter how you break it apart. Just break it apart down all the way to its primes. 16 can be 2 times 8. And 8 can be 2 times 4. And 4 can be 2 times 2. Now that all your numbers are broken apart, let's deal with those variables. So what we're going to do is we're going to expand these variables out. So x to the 4th actually means that there are 4 x's multiplied together. Y to the 9th means there are 9 y's multiplied together. Okay, so with our numbers, I'm looking for pairs of numbers. So here's a pair of 2's. Here's a pair of 2's, and then I have one guy left over that I can't pair up. Well, your variables, you're going to do the same thing. Find pairs of x's. So I have one pair of x's here, and I have another pair of x's here. Then y's, do the same thing. Pair up as many as you can. So one pair, another pair, another pair, another pair, and then one y left hanging out because he doesn't have another pair. Now, all the pairs are going to go out. So one pair of 2's from this guy comes to the outside. Another 2 on the outside. Then I have 2 pairs of x's here. So there's 2 x's that are going to come outside. X times x. I have 1, 2, 3, 4 pairs of y's. So you're going to have 4 y's on the outside. That's all my pairs. Then square root. What's left without a pair? Well, that was this 2 in the very, very, very front. And then this y at the very end as well. Those are left without pairs. Everything's multiplied together. Nothing's being added here. When you're doing radicals, everything is multiplied. Now, let's clean this up a little bit. 2 times 2 makes 4. X times x, I can shorten up into x squared. Y times y times y, I can shorten up into y to the 4th. And then square root of 2y. There's the simplified version of the square root 32 x to the 4th, y to the 9th. So variables act just like numbers do. Break them apart, pair them up, or group them up, whichever you need to do. Let's try example 6. So always start out by finding out which root you have. So in this case, we have a 3, which means we have a cube root, which means we want groups of numbers. Groups of 3 numbers. Okay? So remember, 81, it's a negative, so we're going to break it up into this negative 81 into negative 1 times 81. Now break apart 81. 9 times 9. 3 times 3 for the first 9. 3 times 3 for the second 9. Now your p's and q's you're going to have to break apart also. So p squared means there's 2 p's multiplied together. Q to the 12th means there are 12 q's. Looks like an A. Okay, so now we want groups of 3 numbers. So we're going to group them up. So I see one group of 3's here, and then this 3 does not have a pair. This negative 1 does not have another group. Now try to group your variables. Well, I only have 2 p's, so I cannot make a group of 3 out of those 2 p's. So these are going to have to stay inside my radical. Now my q's, here's a group of 3, here's a group of 3, and another group of 3. So all your groups go outside. So 1, 3 is going to go outside. And then you're going to have 1 Q, 2 Qs, 3 Qs, 4 Qs, all outside. 1 per group. So it's not like you're doing all the individuals go out. It's 1 per group. Then inside that cube root, you still have negative 1 times the 3 that you couldn't take out times the p's that have to stay inside as well. Now let's clean everything up. So 3, 4 q's multiplied together means q to the 4th. Cube root, I'm going to keep negative 1 to the side. 3 and p times p makes p squared. Here's why I kept negative 1 to the side. Just like a couple of examples ago, when you have the cube root of negative 1, remember that is equal to negative 1. That's a perfect cube, so he comes out as well. So it's 3q to the 4th times negative 1 times the cube root of 3p squared. Clean this guy up. Well, 3 times negative 1 makes negative 3q to the 4th times the cube root of 3p squared. This is your final answer here. So when you have a negative under a cube root, remember that comes out because the negative is a perfect cube. Okay? Now, let's talk about fractional exponents. So radicals are actually fractional exponents. So you can convert from one form to the other depending on what you need. Sometimes exponents are easier to work with, sometimes radicals are easier to work with. It just depends on what you have. So we have this formula here to go from one form to the other. This is the exponent form. This is the radical form because there's a radical sign. So here's how this works. The numerator of the exponent is actually the exponent underneath the radical. Then your denominator of your exponent is actually the index of your radical. So the way I have you kind of remember this is I always say exponent over index because it falls in alphabetical order. Because E comes before I, that means E is the top of the fraction and I is the bottom of the fraction. Math likes to be in alphabetical order. Now, if there is no index, remember that it's assumed to be a 2. So let's look at the first example. Rewrite the radical expression in exponential form. So all I'm trying to do is take this radical thing and write it as an exponent. So the a is your base. Well, my base here is what's inside. That's my radicand. So it's just going to be an x. Then, because this 7 is underneath, that's the m, that's your exponent. 4 is the index, that's your n. So it's going to be 7 on top, exponent, over index of a 4. And there's your converted form. Now let's go the other way. Number 2 is rewrite the exponent into radical form. So now I'm starting on this side and I'm working towards my radical. The base is still an x this time. So you're going to have a radical and an x. Now, remember, it's exponent over index. So this is your exponent on the inside. This is your index. So the exponent is the inside. The index is the little outside. And there's your conversion to the other form. Simplify if you can, but in this case, I can't. Example 3. So let's rewrite this radical expression into exponent form. So we have both 18 and x underneath the radical stuck together. So really, there's an imaginary set of parentheses on these guys. Then, if there's not an exponent, we always assume the exponent is a 1. There's also not a radical for this one. So we assume the radical is a 2. So when you go to make this one into exponent form, you need the parentheses. The 1 is the numerator, that's the exponent, so 1 over. 2 is the index, that's the denominator. 18x to the 1/2. So when you have something to the 1/2 power, you're really taking the square root of it. And the last one. Now again, this one's kind of like example 3. You have 2x inside parentheses. So when you draw your radical symbol, you need 2 and x underneath in parentheses. Then this 2 is the inside exponent, so you're going to put 2x squared. This 3 is my index, so it's a cube root. Now let's kind of clean this one up. If you take 2x and square it, you're going to get the cube root. 2 squared makes 4, and x squared makes x. There is your final answer. Now let's put this into practice. Why is this useful? Well, when you have something like example 5, simplify the expression, you could use your exponent rules if you remember them. But if you don't remember what to do with an exponent like this, what you can do is change it into a radical and then simplify that. So all of this goes underneath the radical. So 63x squared y to the 5th, all underneath the radical. The 1 is the exponent inside, so it's 63x squared y to the 5th to the 1st. Then the 2 is the index, tells you what kind of radical you have. So it's a 2. So this is really the square root. Now, anything to the first power, so all of this to the first power is just itself. So you don't really need that first power. You also don't need the little index of a 2, because if there is no index, we assume it's a 2 anyway. So you don't need it. Kind of like putting 1x instead of just x. Now that we have this radical, we're going to simplify. So we need to break down the 63 into, I did 3 times 21. You could have done something different. 3 is prime, but I know 21 is 3 times 7, and both 3 and 7 are prime. So now let's worry about our variables. So x squared means there's 2 x's multiplied together. Y to the 5th means there are 5 y's multiplied together. Now that I have everything expanded, let's go group these things up. So because this is a square root, you want pairs. Square roots mean pairs of numbers. So I have a pair of 3's and a 7 all by itself, 1 pair of x's, and 2 pairs of y's with a y left alone. All the pairs are going out of my root. So 1, 3, I have 1 x, 2 y's, remember one thing per group as a representative, then the square root of whatever's left without a pair. So that would be the 7 and a y. Now, clean it up. So we have 3x, and then y times y makes y squared, square root of 7y. Let's try another one. So simplify this expression. 49z to the 6 all to the 1/2. So again, you could use exponent rules unless you don't remember your exponent rules. It's actually easier for these to be changed into radicals first. So we're going to take this, make it into a radical format. So 49z to the 6th, all in parentheses because it's in parentheses in our exponent form. Then the 1 is the exponent inside, so this is all to the 1st power. The 2 is your index, so I have another square root. So just like before, 49z to the 6th to the 1st is just the same thing as it was before, 49z to the 6th. And the 2 I don't need because the 2 is implied. So let's break this apart. So 49 is 7 times 7, and both 7's are prime. And then z to the 6th means I have 6 z's all multiplied together. Now let's go find pairs. I have a pair of 7's, 1 pair of z's, 2 pairs of z's, and 3 pairs of z's, and nothing left without a pair. So let's talk about what happens when that occurs. So the 7 is going to come out of the root, 3 z's are going to come out of the root, and then normally we would have the square root left over with stuff still inside, but there aren't anything left without a pair. So what that means is your radical disappears. Since there's nothing left without a pair, you have a perfect square, so the radical is going to disappear. So all you have left is this stuff out front. So it's just 7, z times z times z makes z to the 3rd. That's all you have. So when your radical disappears, that's actually the best way for these to work. That's a perfect square, a perfect cube, a perfect fourth, whatever radical you have. Okay, let's try 7. So simplify the expression, 120 a to the 5th, b to the 3rd, all to the 1/3. So again, change this into a radical format, makes it a little bit simpler. So 120 a to the 5th, b to the 3rd, that's the inside part. The 1 is your exponent on the inside. The 3 is the index. Exponent over index. So now this time I have to keep the 3. The 3's stuck. I need the 3, otherwise we would say it's a square root, but this is in fact a cube root. So we're going to take 120, a to the 5th, b to the 3rd, to the 1st, which is just itself. Then simplify this using the same process we've used with the both square roots above. Break down the 120, 12 times 10. 12 is going to be 6 times 2. 6 is going to be 3 times 2. Those are all primes. Now let's talk about the 10. 2 times 5. And those are prime as well. So for a to the 5th, that means there are 5 a's. B to the 3rd means there are 3 b's. So because this is a cube root, that means I need groups of 3 numbers. So the 3 only has a single 3, but I see 3 2's. So 3 and 5 are left alone. I can do one group of A's with 2 left alone and one group of B's. The grouped things go out, so 1, 2 is going to come outside. Then 1A and 1b. Then I still need the cube root of everything without a group. So that would be the 3, the 5, and 2a's. So when we clean this guy up, you have 2ab times the cube root of 3 times 5 makes 15. A times a makes a squared. Lastly, simplify this expression. So this one's a little different because now I don't have a 1 as the numerator. So we're still going to make a radical with it, negative 50x squared underneath. Then the 2 is your exponent, the 3 is your index. So now we have this negative 50x squared all squared, and the 3 is your index telling me I have a cube root. So before we can break this apart, first let's simplify the inside. So negative 50x squared means you're going to multiply that to itself. So negative 50 times negative 50 is a positive 2500. X squared all squared is x to the 4th. So now let's break this apart. Well, 2500, I just did 50 times 50 a minute ago. So let's do 50 times 50. 50 breaks down into 25 times 2. 25 breaks down into 5 times 5. Same thing with this 50 over here. Okay, and then x to the 4th means I have 4 x's all multiplied together. Now that everything's broken apart, let's group things together. So now it's a cube root, so I need groups of 3 numbers. So I have 1, 2, 3 5s. I only have 2 2's though, so these are going to have to stay in, and this extra 5 is going to have to stay in as well. Then I have 3 x's here, so that's one group with 1 x left over. So the grouped things are going to go outside, so that means I have 1 5 on the outside and 1 x on the outside. Cube root of, I have 2 2's left underneath, 1 5 left underneath, and 1 x left underneath. So 5x times the cube root of 2 times 2 makes 4, 4 times 5 makes 20x.